Alright, so this is Chapter 10, Section 8, Geometric Probability. In this section, you will use segment and area models to find probability of events. So this first problem, we're going to use segments to find probability. So point K on ST, so ST goes all the way from here to here, is chosen at random. What is the probability that K lies on QR? So ST is all this distance and QR is just this little nub. So to start us off, I think it's important to mention that probability is equal to the desired outcome divided by all possible outcomes. And then I also think of this as what you want divided by the total. So when we're looking at segments, we want to go, the probability of the point K is going to be on QR, so we use big P to represent probability. We got these parentheses to represent the word of, and then K on QR. So our desired outcome is that we're somewhere in between Q and R. And then our total possible outcome is the length of ST. So the length of QR is 5 minus 8. Absolute value because we're talking about distance. And the length of ST is 2 minus 14, absolute value because once again it's distance. 5 minus 8 is 3. 2 minus 14 is 12, and that is 1/4. Alright, so the probability that K is on line segment QR is 1 out of 4, or 25%. Let me show you how that works on the calculator. So 1 over 4 is the same as 1 divided by 4. It's 0.25, and when we change that to a percent, we move the decimal 2 places to the right to get 25%. All right, next question. A commuter train runs every 25 minutes. If a commuter arrives at the station at random time, what is the probability that the commuter will have to wait at least 10 minutes for the train? So because we're at 25-minute segments, our line segment total is going to be 25. At least 10-minute wait is what we're focusing on. So we're going to assume that each stop takes very little time. We draw your line segment A to B to model the situation. And then the length of the entire segment represents the amount of time between trains. So a commuter will have to wait at least 10 minutes if a commuter arrives at any time between 0 and 15 minutes. So when we look here, if I arrive between 0 and 15 minutes, I'll have to wait at least 10 minutes before the next train comes. This area in between 15 and 20 is going to be less than 10-minute wait. So that looks like this. 10-minute wait is this section. This is our favorable or our desired outcome is this section here. So the probability of waiting at least 10 minutes is our length of our favorable segment, which is 15, and our length of the entire segment, which is 25. So when we reduce that down, it's 3/5, And then calculator work here. 3 divided by 5 is 0.6 or 60%. So remember, we move the decimal place 2 places to the right, and we get 60%. We have a 60% chance of having to wait at least 10 minutes. All right, here is that same problem, just to make sure that it makes sense. So a commuter train runs every 25 minutes. If a commuter arrives at the station at a random time, what is the probability that the commuter will have to wait no more than 5 minutes? So if we take our line segment, we break it up. So let's number it from 0 to 25. And we do 5, 10, 15, 20. Do 5-minute increments. We do want the commuter will have to wait no more than 5 minutes. So if I look, if I arrive right in about this section here, between 20 and 25 minutes, I will have no more than 5 minutes for the train. So when I do my probability, I've got from 20 to 25 is 5 out of a total of 25. That reduces to 1 out of 5. Or 1 divided by 5 is 0.2, which is 20%. So the probability of no more than 5 minutes wait is 20%. All right, we're going to apply the same concept to area. And we're still going to use the property that probability is equal to your desired outcome over your total. So a circle is inscribed in a square. Here's our center. Point Q in the square is chosen at random. What is the probability that Q lies in the shaded region? So that's this little corner here, this little corner, this little corner, this little corner. So we're going to find the probability of the entire square, subtract, so we're going to find the area of the entire square, because that's our total area that we could possibly be in. We're going to subtract out the circle, and then what's left is our desired outcome. So the area of the shaded region is the area of the square minus the area of the circle. So area of a square is 6 times 6. It's base times height. So 6 squared. The area of the circle, just remember, so the distance from here to here is 6. So half of that, which is the radius, is 3. So we replace pi r squared, we replace the r with 3. So now we simplify this down and we get 6 times 6 is 36, 3 times 3 is 9, and I got a pi. Awesome. So we found the area of the shaded region is 36 minus 9 pi. The probability that Q is in our shaded region is the area of the shaded region divided by the area of the square. So the area of the shaded region is 36 minus 9 pi, and the area of the square is 36. Let me show you how I would do that on my calculator, because sometimes half the battle is actually operating in a calculator. So 36 divided by 9 times pi. I would press equals in the middle of this, equals, and then divide it by 36 equals. So we get 0.215, and then remember we move that decimal place 2 spots over to get the probability of Q in the shaded region is 21.5%. So we're going to do one more that's similar to this. So we have a shaded square, and we want to find the probability we're in the shaded region. So here's our operation. We're going to find the area of the square, find the area of the triangle, and then find the area of the shaded region. That's how we're going to roll for now. So the area of the square is 5 times 5. The area of the triangle is 1/2 base, which is 5, times height, which is also 5. Put that in. So our base is 5, and our height was 5. So 1/2 base times height is 12.5. And then the area of the shaded region is the 2 subtracted, the square minus the triangle. 25 minus 12.5 is 12.5. Okay, so now I'm going to tackle this probability. Probability that we're in the shaded region, shaded is 12.5, divided by the total region possible, which is the area of the square, is 1/2, or 50%.